All right, so welcome to Math 349, Operations of Order, lecture, I believe 18. What I want to do today is finish up our unit on Benford's law. This is one of the topics that will be in the Fibonacci book. What I like about it is there's a lot of really good math that can be seen from this. And again, as you start to work on your chapters, if there's math that you are not comfortable with or would like to hear more about, let me know and I will tailor the lectures and stuff like that. Yes. So to publish it, have a final version. Yeah, I'm not going to say that with the camera rolling. I'll talk to you after class. But what I want to do is finish up a little bit of Benford's law, and then for next week, if there are topics that you want me to cover related to what you're doing, let me know so I can make sure to do that. But this is the theme of both books. It's to be a springboard to see good mathematics. And so what I want to do today is talk about the 3x plus 1 problem. Out of curiosity, how many people have ever heard of the 3x plus 1 problem? Okay, excellent. Not everyone has heard of it. So if you've heard about it, just smile a little bit to yourself for a while. So my two favorite quotes about this was Kakutani called it a Soviet conspiracy to slow down American mathematics, because whenever he would travel and tell people about it, they would say, oh, that's not so bad. And then they'd spend a month and become very frustrated afterwards that something so simple was just beyond. And that leads to the second quote, which is by Erdős, who said mathematics is not yet ready for this problem. It turns out this is connected to a tremendous number of really good things. When you are teaching kids, it's a nice example of a way to generate a sequence with something a little bit more exotic than the standard stuff. And so the rule is the following, and this is the fast way of doing it. I take any integer x that's odd, I multiply by 3, add 1, and then I divide by as many powers of 2 as possible. That's what the double division means. It means 2 to the k divides 3x plus 1, but 2 to the k plus 1 doesn't. I'm pulling out the highest power of 2. So what people would normally do is instead they would say, if we send x to the following, 3x plus 1 if odd, or x over 2 if it's even. Okay. So the rule is extremely simple. Take an odd number, multiply by 3 and add 1, take an even number, divide by 2. And so a lot of people say, well, look, why don't we just be more efficient? Let's just assume that x is odd and send x to 3x plus 1 over the highest power of 2 that we can. And just remove all the powers of 2 in one step, and we'll define this as our operation. Okay. There's really no difference between them except for how many steps it takes for certain things to happen. We're just doing all of this now more compactly as one step. And so I actually went to a 4th grade class last week and got the kids playing games with this. So again, at very young ages, people are able to grasp stuff like this. All right. So the conjecture is that no matter what integer you start with, eventually you will iterate to 1. So what happens if you're at 1? Where does 1 iterate to according to this map? What's the next value? Why 2? So is x an odd number? Yes. So I take 1 and I multiply by 3 and add 1, which is, and then I divide by as many powers of 2 as I can. So what would it be? It would be 1. So 1 will just keep iterating to 1 and it will cycle through. If I didn't pull out as many powers of 2 as I could, 1 would go to 4, 4 would go to 2, 2 would go to 1, and then you would cycle. So the conjecture is every number eventually hits 1, and once it hits 1, it stays there. There's no other cycles. Now you could talk about trying to generalize this map. For what other values can we put in here and have something that's always going to be well defined? So you should always be thinking about this whenever you see mathematics. How can I push this forward? What else could I be looking at? So let's do a specific example. Let's do the number 7. So 7 is odd. Multiply by 3 and add 1 is 22. How many powers of 2 can we divide by? 1. So we get to 11. What do you think the subscript 1 means? So one possibility is first iteration. What else? It's the power of k. So both of them are legitimate. Let's look at the next one. 11 is odd. I multiply by 3 and add 134. Divide by 2, 17. Okay, iteration is now looking really good. So it's keeping, oh, not iteration, number of powers of k, not iteration. As we continue, 17 would go to 52, 26, 13. So now we divide by 2 powers of 2. 13 would go to 40, and then 40 goes all the way down to 5. That's going to be 3 powers of 2. And then after that, I would get 5 goes to 16, which collapses down to 1. And so this shows you that if I start with 7, I will eventually iterate down to 1. If you want a challenge, start with the number 27. 27 takes an incredibly long time, much longer than you would expect for a number of that size, to iterate all the way down to 1. Now, this is something that you can talk to little kids. I was in 4th grade and the kids were doing this. And I told them I would give them $1,000 if they can find a number that either goes off to infinity or doesn't iterate to 1. And the kids got very excited. And they said, for the whole class or each, I'll give each of you $1,000. How worried do you think I am? 0, right? The first possible number where this might not be true is at least 10 to the 20. Okay? So how big is 10 to the 20? Okay, but give me something that I can understand. Well, let's do the square root. So if I want the square root of 10 to the 20, 10 to the 10, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, about 10 billion. Can anybody give me something of normal usage around 10 billion? Anything you can think of in the world that's around 10 billion? Market cap of some large companies. What else? Population. Population of the world is about 10 billion. So if I want to get to 10 to the 20, if everybody in the world checks 10 billion numbers, that would basically get me to 10 to the 20. To just give you a sense of just how bad is something like this. I've got a couple of people here I know who are taking computer science classes, and I apologize for using base 10, but you could think about how many operations can your computer do? How long do you expect it would take to check everything by brute force? Now, again, we don't have to check everything by brute force. There's often lots of things we can do. But when you're writing, you want to try to put numbers in perspectives so that people can understand. Saying a number like 10 to the 20, to me, that's hard to process just how bad that is, just how big of a number that is. But everybody in the world checking, 10 to the billion numbers. Yeah, okay. I've got, some sense of just what size things are now. Okay, and so the notation we'll use is we'll talk about the m path of a number. And it's going to just be the tuple that will denote how many powers of 2 have we removed. So the 2 path will just be the first 2 iterations. So it's going to be 1, 1 here. The 5 path would be the first 5, so it would be 1, 1, 2, 3, 4. And in general, it would be K1 through Km. Okay? And so it turns out that we can do some heuristics to get a sense of what's going on. In a lot of things in mathematics, it's going to be very hard to prove theorems. But you might be able to build up some plausible arguments. And so again, what we're doing here right now is not necessarily going to be a direct use to anything you're doing in writing, but this idea of how do we build some intuition? How do we get a sense of how likely something is? That's extremely valuable. The 3x plus 1 is a completely deterministic problem. You give me a number, and once you give me that number, everything is determined. It's odd, so I multiply by 3 and add 1, pull out as many powers of 2, keep doing this. And eventually it should either hit 1, go into some other cycle, or go off to infinity, and I just keep computing. There's no challenge left. There's no difficulty, right? It's not hard to keep finding more iterations. It's just time consuming. Now, to figure out exactly what happens if I tell you the number, it turns out that the arithmetic structure of the number does give you some information about what's happening, and there are formulas that tell us what the starting empaths will translate to. So if you give me, I really like 11357218811, I can tell you all the numbers whose empath starts off like that. So there are some results that we have. But in general, to analyze an arbitrary number is hard. So what we can do is we can say, let's try to come up with a probabilistic model. And this is a really good skill to get, is to get a feel for what's going on. So rather than doing things deterministically, let's just try to do things on random. How many of you have taken a probability class? Okay, I can give you a lot of very difficult problems. And you might be able to write down the answer by using combinatorics. I want to figure out how often does something happen in a game of cards. Another thing you can do is just play a lot of games of cards and just keep track. How many is a lot? Okay, well, if we play every single game of cards, we're going to run out of time. The universe dies of a heat death. If we just play a couple of hands, that's not going to be enough. But I can easily set up my computer to do 10 million, 100 million hands, and that would be a really good estimate for the answer. So there's an exact formula that I can get with combinatorics, but I can also just run some code and get a feel for what's going on. Out of curiosity, does anybody know the card game cribbage? Okay, so my daughter and I have been playing a lot of cribbage lately. This is one of the things you do when you are stuck on a couch, and it's not a high intense game. And we've been a little bit curious about how many points on average can you get on a good hand. And so we're going to now just start keeping track of how many points. We'll get some data. We're going to be probably playing a lot over the next month, so we actually should probably get a good amount of data. But it'd be much better to write a computer program and get a million billion games done very quickly. If I give you a number, what do you think the probability is that it's even? About 50%. What if I tell you my number is odd? What's the probability now? 0, right? This is who's awake right now, right? Okay, so if the number is odd, it has 0 probability of being even. If I take my odd number and I multiply by 3 and add 1, what's the probability that it's even? So I take an odd number, I multiply by 3 and I add 1. What? 100%, okay? Now, what fraction of the time do you think this new even number, 3x plus 1, is divisible by 2 and not 4? So we know it's an even number. How often do you think it's divisible by 2 but not by 4? 50%. Half of the even numbers are multiples of 2 and not multiples of 4. What fraction of the time do you think it's a multiple of 4 but not a multiple of 8? 25%. Or 50% of what's left over. So depending on how you interpret it, 50% of what's left over or 25% of what I initially had. And that's where this analysis comes from. Let's let an plus 1 be my map applied to an. And let me try to figure out on average what's happening. So that's what this funny looking E is. It's the expected value. And it turns out that instead of looking at the number, I should really be looking at the log of the number and trying to understand the logarithm. And I'm going to look at, on average, where do I expect the logarithm of my number to be? This is a multiplicative process. It's not that unreasonable to expect that. So the log of where I am after one iteration is going to be related to where I was. So my number was an, I multiply by 3, I add 1, and I divide by some number of powers of 2. I'm not going to really worry about the plus 1. You've got to imagine A has like a billion digits. So adding 1 at the end is not really going to affect my expected value. It's going to be much easier to analyze like this. And then what I'm going to do is I'm going to weight what fraction of the time is it divisible by 2 but not 4, by 4 but not 8. Yes. Well, because right now I'm just trying to get a rough sense of the size. I just care about the size of the number, and I want to roughly see what is the size of one iteration further down the line. Do I expect numbers to be growing or do I expect numbers to be decaying? If we believe that eventually every number iterates to 1, then what do you think should be happening to the size of the numbers as we iterate? It should be decaying. It doesn't always decay. Can somebody give me a number where when you apply the 3x plus 1 number map, it's larger after you apply it than when you started? So if I give you 5, 5 iterates to 1, because 3 times 5 plus 1 is 16. Pull out all the 2's, I go down to 1. So can you give me a number which is larger? So good. So 7 goes to 11. So it can sometimes get larger. And it could get larger by roughly a factor of 3/2. If it gets small, it's going to get smaller by either a factor of 3/4, 3/8, 3/16, 3/32, and so on and so on and so on. So what we are doing here is we're trying to figure out, on average, how large do I expect to be one iteration later? So I take my number, I multiply by 3, and I divide by some number of powers of 2. If k equals 1, I'm only dividing by 1 power of 2. How often did we say that happens? So how often do we divide only by 2? Half the time. And that's why I have a 1/2 over here.
And it gets large by 3/2 at that.
Exactly. And then if k equals 2, I would get 3/4, and I would weight it by 1/4. If k equals 3, I would have 3/8 of where I was, and I'd multiply that by 1/8, and so on and so on and so on. So this is going to give me the expected value of the logarithm of one future step based on where I was. So now I just have a sum that I need to evaluate. Well, this is going to be the log of an plus the log of 3 minus the log of 2. And then I'll have the sum of k over 2 to the k by just using some log laws to figure out what the sum is. Does that sum look familiar? Have we seen that before? So we have, the sum. Okay, goes to, let me just make sure I start at the same place. We're starting at 1. Okay. So the sum goes from 1 to infinity of k over 2 to the k. Or if you want to, could I start the sum at 0? It's fine to start it at 0, because if if k equals 0, that's no contribution. Have we seen this sum before? It's related to the geometric series. So the geometric series was, the sum, k goes from 0 to infinity of x to the k is 1 minus x to the negative 1 if the absolute value of x is less than 1. And then what did we do to both sides? Anybody remember what we did? So we want to have k divided by 2 to the k. This kind of looks like a geometric series. What would you say the ratio is in this? 1/2. So the ratio looks like it's 1/2. How would I get a k from this? I want not just the sum of x to the k, but kx to the k. How could I get that? Not logarithm. What can I do to the sequence to bring down a k? Not integrate, differentiate, right? And I'm going to take x d by dx of both sides. Because if I take the derivative, I would get k x to the k minus 1. And then if I multiply by by x, I restore the power of x to what it was before. This now connects to the operations of order. When can I switch the order of operations? When can I say the derivative of an infinite sum is the infinite sum of the derivatives? This is a key result we need. If I do that, I now get the sum, k goes from 0 to infinity, of k x to the k. And when you do all this stuff over here, you'll get x over 1 minus x squared. So when you do the algebra, this is what you get. We now have a formula. Just take, if, that's a terrible if x equals 1/2, we get 2. So we get 1/2 divided by 1/4, which is just 2. We actually have a formula for that sum. I could do the sum of k squared over 2 to the k. We could actually use this to calculate variances as well as expected values. So we talked about stuff like this when we were doing method of moments. And it's nice to see the same mathematics occurring in many different places. And again, that's one of the things I want you to see in a class like this. This is supposed to be a springboard to seeing good mathematics. It is hard to prove identities, to find identities. Differentiating identities gives you infinitely many new identities from one fixed one. That's extremely powerful. And so now that we have that, we can come over here and we know the sum of k to the k is just 2. So we have the log of an plus the log of 3 minus 2 log 2. Well, 2 log 2 is the same as log 4. So this is the same as the log of 3/4. Why is the log of 3/4 less than 1? Who remembers their logarithms? It's a log of 3 minus the log of 4. And your log is an increasing function, so that's one way to interpret it. What number has a logarithm of 0? 1. And so anything greater than 1 is going to have a logarithm that's positive. Anything less than 1 is going to have a logarithm that's negative. So what this is telling us is, look, on average, 1 iteration later, you should be a little bit smaller. We could even predict about how many iterations you need before you should hit 1. Every time I'm making myself small by a little bit like this, okay, well, I can figure out how many multiples of this do I need to get to the log of an. And that should be a really good predictor for how many steps it takes to iterate down to 1. And when you do the numerical experiments, it turns out beautiful. All right, so back in 2005, I was working with a friend of mine. What should I want to say? We found ourselves at a conference in a very nice part of the world, and we were feeling a little guilty about all the money that was being spent to bring us here. So we decided we should do some real mathematics to feel better about being here. And so we proved the following result after a lot of work. So xm is where we expect to be after m iterations. So each time we expect to be decreasing by a factor of 3/4. I'm sorry. xm is where you are after m iterations. We divide by where you expect to be, and we were able to show that this converges to Benford. Some of our friends, after I gave a talk about this at Michigan, they proved a lot more. They showed that, translating from math speak, if you take a huge range of consecutive integers from the beginning, and you take a very small epsilon, so I want to be within epsilon of the Benford probabilities. They said almost all of your starting seeds, as you look at their decay paths, will be very, very close. They'll be within that tolerance of Benford. And to just look at some data, here what we're doing is we're looking at 80,540 iterations of a random 10,000 digit number. And just looking at how many steps do I need before I would expect to iterate down to 1, theory predicts it should take 80,319. It took 80,514. So this heuristic at least was doing a pretty good job in this one specific case. Just because it works well once does not mean it's always going to work, but you can do simulations like this. And it turns out these random models can often model these deterministic processes very well. And we look at the prediction of the observed versus the Benford, those should look like pretty good fits. Anybody have any thoughts about how you would work with a 10,000 digit number? Computer, how? Who are my computer scientists? Do you want to have a 10,000 digit integer and work with that? I'm sorry? Modular what? To some extent, when you're doing a lot of iterations like this, if I write my number in binary, which we all know is a great way to represent numbers, when you multiply by 3, how would you multiply by 3 in binary? I'm sorry? Oh, okay. So basically, the way you would multiply by 3 is you multiply by 2, and then you add back your number. If you write your number in binary, what does multiplying by 2 do to your number? It shifts everything left. So has everybody here used binary? Okay. So people are comfortable with base 10, yes? So if I want to do things in binary, I would maybe do things like a3 times 2 cubed plus a2 times 2 squared plus a1 times 2 plus a0 times 1. This would be writing a number in binary. So I'm writing things in base 2. So in base 10, I would be using, instead of 2, I'd be using 10. And any number can be written in binary. So you give me a number, and what I do is I look at the highest power of 2 that's less than or equal to my number. So for instance, let's say I'm given the number 67. Well, let's do 57. 57 would be a little bit more fun. So what is the highest power of 2 less than or equal to 57? 32. And 32 is 2 to the 5th, right? So I would have 1 2 to the 5th. So 57 minus 32 is 25. Do I have any 16s? Yes. So I would have 116 1 times 2 to the 4th. 25 minus 16 is 9. Would I have, what's after 16 is 8? Would I have any 8s? Yep, so I have 1 8. So 1 times 2 cubed. 9 minus 8 is 1. Would I have any 4s? No, so it would have 0 times 2 squared plus 0 times 2 to the 1st plus 1 times 2 to the 0. And so 57, I can write it as 1 1 1 0 0 1, and I put a subscript 2 there to tell myself that I'm writing it in base 2. So this is binary. And so if I just give you the number 111001, you don't know what base is that. What's your default assumption when you see a number written? Base 10. And so we put a little subscript 2 to remind ourselves that this is base 2 now. Well, if I were to multiply a number by 10 in base 10, we're just adding a 0 at the end, right? If I multiply a number by 2, I'm just adding essentially a 0 at the end. So if I give you the number 111001 base 2, and I multiply this by 2, 2 is now going to be written as 10. This just becomes 111010 base 2. So if I want to multiply a number and it's written in binary by 3, if I just multiply by 2 and then add back the original number, that is the same as multiplying by 3. And it's very easy to multiply by 2 base 2. It's easy to multiply by 10 base 10. It's easy to multiply by b base b. All you're doing is you're shifting. It's just a left shift. So I just shift and then add. So a really good way to work with numbers like this is to just have numbers in an array. If you write your number as an array, you can do these operations very easily. Now, what about dividing by 2? Is that easy or hard in binary? Yeah, you just write shift 1. If the number is a multiple of 2, what must be true about the final digit? Has to be a 0, so just chop it off. So it's very easy in binary to multiply by 2 or to divide by 2. Now, if I want to do things base 10, because I care about the first digit, this is a nice question. So let's say I give you the number 34298 well, that's type of 6, 71, and I want to multiply by 3 and add 1. Do we all agree that that's easy to do base 10? Multiplication is not that hard. But now I want to divide by 2. That's harder. I can't just chop off the digit, right? Does anybody know an easy way to divide by 2? What base are we working with? 10. So Your default should always be, think of yourself as a candidate for president. Okay, when you're asked a question, does the candidate answer the question that's asked? No, they go into their prepared spiel. Depending on how good they are, they can try to tie that to what you asked. And they meander for a little bit, and then they get to the set piece that they wanted to work in. If we're doing things base 10, what division would you love to do base 10? 10. I'm asking you to do division base 2. So instead of dividing by 2, what could you divide by? So how could we make this look like a division by 10? Divide by 10. Yeah, so if I take this and I'll put it a little bit darker and I multiply by 5/5, now all of a sudden I'm dividing by 10. And we know multiplying by 5 is very easy to do. I just take my array and just march down the digits. So if you wanted to, we could actually change this to multiply by 15 and add 5. How would you multiply by 15? You could do that as just a shift, which is 10, and then multiply by 5 if you want. There's lots of things you could do. So the thing I want you to get out of this is, depending on what you're trying to do, there's often more than one way to do it. And if you care about efficiency, if you care about speed, a lot of times the way you've been trained to do things is not the best way to do it. This is one of the biggest differences between applied mathematics and pure mathematics. If I'm doing things theoretically, I can say, oh, just factor the number. Okay, well, from a practical point of view, we don't know good ways to factor numbers. And that's why a lot of modern e-commerce is possible, because we can have security systems for stuff like this. So over here, this was looking at 80,000 plus iterations of a 10,000 random digit number. I've worked with 100,000 digit random numbers. It's not that hard to do. You just have to have a long array, and you just do very simple operations on an array. I don't need a high-level programming language to do this. This is a very similar problem, except now what I'm doing is there's only one small difference. If you look very carefully between the top here and the top here, there's one symbol that's different. Does anybody notice the different symbol? Really carefully. Yes, so over here, I'm pulling out as many powers of 2 as I can in one step. And in this one, I am not. And so that's why I have many more iterations over here. And again, looks beautifully Benford. Instead of doing the 3x plus 1 problem, we could do the 5x plus 1 problem. And if you think back to what we did before, we had the log of 3/4, which was negative. What do you think we would have for the 5x plus 1 problem? So if you think back to the analysis we did, oh, I had it, then it moved back one. So when you think back to the analysis we did, what do you think the log of 3/4 would become if we look at the 5x plus 1 problem? Log of 5/4. And what can you tell me about the log of 5/4? Greater than 1. So what do you expect would happen as we keep iterating with the 5x plus 1 map? Yeah, so you would expect it would probably escape to infinity. It's not a proof, but by looking at this logic, I wouldn't be surprised if that happened. And so here, I'm not saying it iterates to 1. I'm just looking at the same, a good number of iterations of these. And again, I'm seeing things that are extremely close to Benford. Okay, so this is a lot of really good stuff on 3x plus 1, a sequence that is very easy for people to understand. The rule is very simple. The analysis becomes quite difficult. And when you're writing books, you want to try to find ways to take the exciting stuff and make it accessible to people who are reading it so that they can see, where will things go if you continue this? What are you going to eventually start to see? And so for some of the things you're doing, it's going to be easier than others. Then the question becomes, what techniques do we need to analyze things? And a lot of times the math we need to analyze, or at least the math we think we need, is a lot more involved than the math we need to state. So everybody should have heard of prime numbers. It's believed that there are infinitely many primes that differ by 2. It's believed that every sufficiently large even number can be written as the sum of 2 primes. So somebody want to give me a reasonable even number? 12. All right, so I could write 12 as 5 plus 7. And if I tried to use 3, I would have to use 9. That doesn't work. So that's the only way to do 12. Someone give me another even number. 22. So for 22, I could write it as 11 plus 11. Now the next number, if I go below 11, would be 7. So I would have to do 7 plus 15. That's not going to work. If I did 5, it would have to be 5 plus 17. That works. So we now already see that some numbers could have more than one way of doing it. It turns out that as the number gets larger, we actually have a predicted formula for how many ways you can write an even number as the sum of 2 primes. No one knows how to prove that every even number can be written as the sum of 2 primes. We have some methods that we like a lot that give us a wonderful heuristic as to what the answer should be, but they're not proofs. They suggest what the answer is, but it's not a proof. No, it's that we can't show that the error term is smaller than the main term. We have a beautiful prediction for what the main term is, and we have what we believe is a lower order correction term. We just can't prove that it's truly lower order. The only way we know how to estimate it gives a really bad bound on it. We have a terrible bound on the truth, and that's the problem. But we believe every sufficiently large even number, and sufficiently large means at least 4. That should be far enough for it to work. But we can't prove it. But we can state this in such a way that somebody in elementary school, middle school can easily understand the question. Can I write every even number as the sum of 2 primes? The mathematics we start to use to solve it becomes very hard. And so when you're writing things up, whenever possible, you want to try to give a sense of what comes next. What are the ingredients we need to solve this? Especially if we're writing a book, it's nice if different chapters in the book relate to each other. You can say, hey, remember earlier in chapter 5 when we introduced differentiating identities? We're going to use that again. Okay, and so here we got some data, and again, this is not a proof that it's Benford, but it's quite likely. So what I want for the last couple of minutes is talk just a little bit more about gathering some data, and then this will end the Benford unit. So this was inspired by a paper in physics, and I worked on this with some students here, including a colleague of mine, Professor Stark, in the physics department. If people would like to drop watermelons to try to build intuition for something like this, or if there's other things you want to drop, let me know. Happy to advance the cause of science. So we're doing some kind of decomposition process. So imagine you have a stick of length L, and we're going to choose some probability P. Let's say we choose it uniformly in the interval 0, 1. So every number is as likely to be chosen as every other number. And then we're going to break the stick into 2 pieces, P times L and 1 minus P times L. And then lather, rinse, repeat. We keep doing this. Now, there's a couple of ways to keep doing this. One way is we choose 1 P at the very beginning, and then for each subsequent piece, we always break it using that P. The other way is every time we have a piece, we get to choose a new probability. Let's do this special case when we always use the same probability. So once we choose a P, we always have a P. And we're going to repeat this n times. And then the question is going to be, what's going to be true about the lengths of these sticks? Do you think that it's going to be Benford? As we do more and more levels, as we go further and further down, as we have more and more pieces, how many pieces will we have after n levels? So the first level, we had 1 piece. Then we break it. We now have 2 pieces. We break those. How many would we have? 2 to the n. So the number of pieces is exploding. So do you think it's always going to be Benford? Never going to be Benford? Very rarely going to be Benford? Most of the time going to be Benford? At least once not Benford? Okay, can you give me a choice of P that will not be Benford? 0.5, excellent. What's true about the stick lengths if you choose 1/2? It's uniform, they're all the same. So if you take p equals 1/2, clearly it can't be Benford. And we're not going to choose p to be 0 or 1 because then we're not doing anything. So the question is, if we stay away from 1/2, as we take more and more breaks, will we get Benfordness? Now, one thing to note is if I break it into p and 1 minus p and then break it again, two of the pieces are actually going to have the same length. So even though I have a lot of different stick lengths, I don't necessarily have a lot of different distinct stick lengths. At this level, I actually only have 3 distinct lengths, not 4. In the next level, and as I go down further and further and further, you're actually only going to have, I believe, n+1 distinct stick lengths. And certain lengths are going to be more likely to occur than others. And so here is an example when p equals 0.51. So I chose something close to 50%, but not at 50%. And you can see it looks pretty close to Benford. I also chose something very close to 100%. I chose p to be 0.99. And again, very close to Benford. Are you convinced? Is it always going to be Benford as long as we stay away from 1/2? So if you've been in a class of mine before and you've seen this, please don't speak up. I want to check people's algebra. 16/64. I'm sorry? 1/4, good. 19/95. Good. Let's do a harder one, 49/98. 1/2, let's do one more. Let's do 12/24. I get 1/4. Does everybody get 1/2? Is it just me? My daughter had a bad night. I'm a little low on sleep. Let me show my algebra. 16/64, cancel the 6s, and you get 1/4. 19/95, cancel the 9s, get 1/5. 49/98, cancel the 9s, get 4/8, which reduces to 1/2. Therefore, clearly, I cancel the 2s and get 12/24 is 1/4. Right? No. There's no such thing as proof by example. There is proof by exhaustion, where you show every single case works. So just because I've shown you some data does not mean I've proven anything. Now, the question is, at some point, you start to become more and more confident. The more data I show you, the more likely you are to believe me. What would make you more likely to believe me rather than my showing you more choices of p? A proof, but what else? So if you want to see, I'll choose another 100 values of p. Would that be convincing to you if I choose another 100 values of p? So maybe I'm deliberately choosing certain values of p, right? I have plenty of choices of p that I know it's going to be Benford, and I might know which ones are not going to work, and I can deliberately stay away from them. So here is p equals 1/11. Okay, so these are still the same plots as before. This is not the plot of 1/11. I think we have the plot of that later. All right, here's the plot of 3/11ths, which is not too bad from Benford. For real data, I wouldn't be surprised with fluctuations like that. Here is p equals 1/11. I knew we had the plot somewhere else. And so if you look at the plot, do we agree that the dots do not look like they're following Benford? Yeah. Yes. So the question is, where does this come from? And without going through all the details of the proof, I can actually give you a quick, rough sense of what's going on. A lot of it comes down to how do we write our numbers? And so much of mathematics is trying to find the right way to view something. So if I look at my stick lengths, they're going to be of the form p to the k, 1 minus p to the n minus k. And how many times will I have that length? If I have n levels, Does anybody remember their combinatorics? How many times will I have this? N choose k. So I'll have this n choose k times. Okay. So n choose k times, this is going to be my stick length. And we've talked a little bit before about what does n choose k converge to? Is there a Gaussian around there? Another way of writing this, do you see how I have a 1 minus p to the n and I have a negative k? Let's put everything with a k together and pull out the 1 minus p to the n because that's independent of k. I can write this as 1 minus p to the n times p over 1 minus p to the k. And what's happening is every time I go down, let's call p over 1 minus p, let's call that maybe r. I start with 1 minus p to the n. Then the next is going to be 1 minus p to the n times r, 1 minus p to the n times r squared, dot, dot, dot. When I look at the stick lengths, to get from one length to the next, I'm just multiplying by r. What would be a value of r where you know it can't be Benford? 0. What else? 1. What else? Where they're all going to have the same first digit base 10. What value of r would make sure they all have the same value, the same first digit base 10? 10. What else would have the same? 10 would work. What else would work? Any power of 10. What if this ratio was the square root of 10? Then I would have my number times the square root of 10, and then I have my number times 10. It would be cyclic. So if r is 10 to a rational power, you're going to cycle. And that's what's going on. So if we look at what's going on over here, I have 1 minus, I'm using j rather than k. I'm moving by that fixed factor. And so if 1 minus p over p is 10 to a rational number, I'm not going to be Benford. So it's actually trivial to prove that you're not Benford for those probabilities. It's much more work to prove that you're Benford for the other ones. But this is how I know exactly what to take for my p to get a nice, non-Benford behavior. I know what the general theory is. I know which p's to take. I know which p's to stay away from. When someone is showing you things, you always want to be skeptical as to they're choosing things. Yeah, no. I'd like some say in terms of what you're looking at to provide intuition. All right, so this is a good place to stop for today.